Section 5 is going to cover two more gas laws, Graham's law and Dalton's law. Graham's law deals with the movement of gases, how fast they're moving. So if you remember from earlier in this unit, we talked about effusion. That's the movement of gas through a small opening in a pressurized container. And so if you ask yourself, do gases move at different rates? Well, at the same temperature, different gases do move at different rates. That goes back to the equation for kinetic energy, 1/2 mv squared. Okay, so in order for them to have the same kinetic energy, i.e. temperature, then if you have a different mass, then the velocities must be different. Okay, so therefore gases at the same temperature must be moving at different rates if they have different masses, different molar masses. So how is this useful? Which gases move faster, which ones move slower? Thomas Graham determined an inverse relationship between fusion rates and molar masses. So it's inverse relationship, right? Meaning, so as molar mass, say, would go up, then velocity would go down, okay? It means that the heavier something is, the slower it moves. The lighter something is, the faster it moves. So lighter gases move faster, heavier gases move slower. And he figured out that the rate here, actually, this comes from the equation for kinetic energy is actually what we're doing here. It's this little symbol means proportional to. The rate of effusion is proportional to 1 over the square root of the molar mass. So without having to do any real thinking here, we can figure out which gas is moving faster, helium or xenon. Which is it? It should be, right, helium. It's the lighter gas, okay? It's got a molar mass of 4. I'm not sure what xenon is off the top of my head, but it's significantly higher than helium. And so we said just a moment ago that lighter gases travel faster. Heavier gases, like xenon, would travel slower. Well, rather than just a proportional to statement, Graham developed a law as applied to diffusion. So what it's going to do is it's going to compare two gases and their rate of diffusion, okay? Moving a material, one material through another, right? From high concentration to low concentration. And so really what this is just rearranging the equation for kinetic energy if these things are at the same temperature. So we're not going to go through that whole derivation here. It's good enough that you just see this. And that's the rate of gas A divided by the rate of gas B is equal to the square root of the molar mass of B over the molar mass of A. Most common mistake in this equation is putting both the A's on the top and both the B's on the bottom. It doesn't really matter which one you make, gas A or B, as long as you have them correctly flipped from each other in this equation. However, I tend to make gas A the lighter gas since it will be going faster. So that means your rate A over rate B will have a value greater than 1 when you are calculating it. It'll make a little bit more sense to do that. So generally, I make A the lighter gas. You don't have to do that, but it might make your math a little bit easier here. So we're going to try some equations with this and see how we do. Okay, so here's a sample problem. Ammonia has a molar mass of 17.04 grams per mole. Hydrogen chloride has a molar mass of 36.46 grams per mole. What is the ratio of their diffusion rates? So here's our equation. Rate A over rate B equals the square root of molar mass of B over the molar mass of A. I went ahead and made ammonia A since it's the lighter gas. You don't have to do that, but it will make our math make a little bit more sense here. So let's go ahead and just plug stuff in. Here we have the rate of, we'll call it NH3 now, divided by the rate of HCl is equal to the square root of, okay, it's molar mass of B on the top, so 36.46 grams per mole, and on the bottom will be the 17.04 grams per mole. Plugging that into a calculator, 36.46 divided by 17.04, and then taking the square root of that, this gives us 1.463, let's call it, 4 significant figures. It will not have any units because grams and moles all cancel out here. This value is unitless. What does this actually mean? This means that at the same temperature, ammonia gas compared to HCl is moving 1.463 times faster. So ammonia is 1.463 times faster than HCl. If you wanted to, you could put underneath this over 1 if it helps you remember that this relative HCl relative to NH3 is 1, and NH3 would be 1.463, but there's no unit here. Okay, let's try this problem. In a sealed container, carbon dioxide is moving at 455 meters per second. In the same container, how fast would helium gas travel? So using our equation here, we're going to set A as helium and B as carbon dioxide since helium is lighter. So rate A over rate B equals square root of molar mass of B over A. Rate of helium will be on the top, rate of CO2 is on the bottom, equal to the square root of molar mass of CO2 divided by the molar mass of helium. So we're solving for the rate of helium is equal to, okay, well, we'll bring the rate of CO2 over to the right side, and then times molar mass of CO2, square root of molar mass of CO2 divided by the molar mass of helium. And we start plugging stuff in. This is 455 meters per second. And then here we're going to have the square root of 44.01, okay, divided by 4.00. Running out of room for the units, so we'll skip writing them just for the moment. Okay, and plugging that in, okay, that's square root of 44.01 divided by 4, so almost 11 on the dot. Take the square root of that, and then multiply times 455. And we're going to round this to 3 significant figures. That is 1,510 meters per second. And let's stop to see if that actually makes sense, right? Helium is the lighter gas. It's got a molar mass of 4. It should be moving faster. The lighter gases move faster. Well, carbon dioxide has a molar mass of 44.01. It's moving at 455. It's moving slower. So yes, this does check out. Okay, we're going to try a related one here and see how we do. So this one says it takes a sample of SF4 gas 244 seconds to travel some distance. How long would it take N2O gas to travel the same distance? Well, this time around we have to remember that rate is not the same thing as time. Here we are given 244 seconds. So since rate is equal to distance divided by time, we can show that as R equals D over T. And instead of writing rate A over rate B, we're going to substitute in distance and time and see what happens here. Because we can't just plug in time. We'd actually get the wrong answer if we plug in time where it says distance. So what I'm going to do is actually take this D over T, and we're going to sub it in, okay, for both A and B here. And let's see what happens. So instead of rate A, we're going to have distance of A divided by time of A, all divided by the distance of B divided by the time of B is equal to the square root of molar mass of B over the molar mass of A. So the right side of the equation doesn't change. And all I did here instead of rate A over rate B is distance of A divided by time of A, all divided by distance of B over time of B. Well, if I'm dividing by a fraction, that is like multiplying by a reciprocal. So what we're going to do is we're actually going to flip this and multiply by it. So if we rewrite this now, we're going to have dA over TA times TB over DB is equal to square root of molar mass of B over molar mass of A. So from this, okay, we're getting closer to some solution. I'm going to actually write this all the way up here now. But it says, right, to travel some distance, how long would it take N2O gas to travel the same distance? Well, in this particular problem, okay, what we are assuming is that dA is equal to dB. And if that's true in this equation here that I have of dA times TB over TA times dB is equal to the root of molar mass of B over the molar mass of A. If that's true, dA and dB are going to cancel. And what I'm left with then is the equation of time of B over time of A equals the square root of molar mass of B over molar mass of A. Notice how this equation here is different than the one where it is with rate. With rate, it was rate A over rate B. And with time, it's now time of B over time of A. So make sure we're paying attention to what sort of numbers we're being given to start with. And now if we look into what we should put stuff with, we're going to make SF4 our B gas and N2O our A gas. So what we end up with here is 244 seconds, okay, over the time of N2O is equal to the square root of the molar masses of these gases. On the top, SF4 has a molar mass of 108.07, and on the bottom, N2O has a molar mass of 44.02. And if I rearrange this for in time it takes for N2O, we get 244 divided by 1.567. So we'll call it 1.567, which is this half of the expression. So we're just bringing it to the bottom and bringing the time of N2O up on the top. So 244 divided by 1.567 is 156. Oh, let's change that back to the pen. 156 seconds. Not a very good 5 there. Let's stop and make sure that this actually makes sense. 156 seconds. There we go. So let's make sure this makes sense. N2O is lighter. It should be traveling faster. If you're traveling faster, it should take you less time to go the same distance, which seems to be the case here. So at least logically, our answer seems to be consistent. Okay, here's one for you to try. If neon gas is moving at 826 meters per second, how fast is I2 gas moving? So we're assuming here, obviously, that the iodine is in the gas form, so it's been heated up slightly. So give this one a try. Let's see how you do. Okay, so making neon gas A, since it's faster, and I2 gas B, we set up our expression from Graham's law like this. Plug in 826 for the rate of neon. We're going to end up solving for the rate of I2 is equal to the square root of, okay, the molar mass of I2 is 253.80, divided by the molar mass of neon, which is 20.18. Rearranging this whole thing, we get 233 meters per second, which should make sense. It is a heavier gas. I2 would be a heavier gas. It should be moving a lot slower than neon, which it is. Our second law here is called Dalton's law. This is the same John Dalton from Dalton's atomic theory from the early 1800s. So he did a lot of stuff in terms of the world of chemistry. Anyways, Dalton determined that each gas, if we have a mixture of gases, exerts pressure independently of the other gases present. So this is if you've got a container with multiple types of gases in it. And what he formulates is called Dalton's law of partial pressures. That is, the total pressure of a mixture of gases is equal to the sum of the pressures of all the gases in the mixture. So total pressure is equal to the sum of pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3 plus the pressure of whatever number of gases there are. If you've got 12 gases, then you'd have 12 terms here. If you've got 2 gases, you would only have 2 terms. So this is the pressure of each of those gases add up to the total pressure. Now, oftentimes, this is going to get paired up with the ideal gas law, especially in an equation that you'd be solving for pressure, okay? The example you're going to see here on the next slide is about as easy of a Dalton's law problem as you could ever get. The ones you'd have for homework will probably have a little bit more difficulty to them, but remember that the pressure here can be calculated by nRT over V, okay? So on homework problems, maybe make a note of that if you think you're getting stuck on a Dalton's law problem. Okay, so let's look at this one. Like I said, it's about as easy of a problem for Dalton's law as you could possibly get. A mixture of O2, CO2, and N2 has a total pressure of 0.97 atmospheres. What is the partial pressure of O2 if the partial pressure of CO2 is 0.70 atmospheres and the partial pressure of N2 is 0.12 atmospheres? So setting up our equation, right, we have three gases here, so our total pressure is going to be the sum of the pressure of oxygen plus the pressure of CO2 plus the pressure of N2. Okay? It tells us that the total pressure is 0.97 atmospheres. And that's equal to, okay, the partial pressure of, it says what is the partial pressure of oxygen? So that's what we're solving for. It gives us the partial pressure of CO2 is 0.70 atmospheres plus, and then for nitrogen it is 0.12 atmospheres. And all we really have to do here is just some simple algebra rearrangement. We'll have 0.97 minus 0.7 minus 0.12, and we'll get this to the hundredths place of 0.15 atmospheres. Like I said, it really can't possibly get any easier than this in terms of a Dalton's law problem, because the pressures are all given to you, and you would just have to solve for the one that you don't know. Okay? If I had 4 gases in this problem, I would have 4 terms here. If I had 2 gases in this problem, I would only have 2 here. So this one's pretty easy. I'll give you a slightly more difficult one here to see how you do. Okay, so this is a little bit harder. We'll see if you can figure this out on your own. A 5.00 liter container with a total pressure of 3.25 atmospheres contains 2 gases, CO2 and O2. If the partial pressure of CO2 is 1.50 atmospheres and the container is at 300 Kelvin, what is the mass of O2 in the container? So keep in mind here, I told you that generally with Dalton's law, you oftentimes pair this with the ideal gas law. So that's my hint to help you get to the answer here. Okay, so here's the solution. We start with Dalton's law. The total pressure is equal to the pressure of CO2 plus the pressure of O2. And we can solve that for the pressure of oxygen by plugging in those values. Subtract 1.50 from 3.25. That gives us the pressure of oxygen is 1.75 atmospheres. From there, to find the mass of oxygen, we use the ideal gas law, and we will substitute, or not substitute, we'll solve for N. So we'll bring RT over to this side. PV over RT. Plug in the value of 1.75 atmospheres for the pressure of oxygen. The volume of the container is still 5 liters, so that doesn't change. R never changes. And T is 300 Kelvin. That gives us 0.355 moles. And then to get the mass, you just multiply times the molar mass of oxygen, which is 32.00. And we get 11.4 grams of O2. So hopefully you did okay with that one. It's a little trickier, but your homework problems might look more like this than that easier one that was on the previous slide.